Hey everybody, welcome back to physics. Today we're actually going to be starting a new unit. We're going to put magnetism aside and we're going to start our study of waves. Now we are actually approaching the end of our study of physics. And at this point it's good to take a step back and see what we've covered so far. We've discussed where things are. We discussed how they're moving. We discussed how their motion changes. We discussed what happens when these things collide with one another. We discussed how energy gets changed when we move a particle from like one location to another, or how if it speeds up, slows down, how the energy changes. So how does this universe look so far that we built? Well, the universe we built right now is dark. There's no light in this universe that we built with in our physics topic so far. And the universe we built is quiet. There's no sound, there's no light. So what makes our universe so colorful and what makes it so musical? In order to fill in those gaps, to understand how the universe looks and sounds, we need to talk about how waves work. So we're going to talk about the basics of waves, what waves are, what are the characteristics of waves, and we'll talk about particular types of waves, sound waves, light waves, and what do waves actually do for our universe? Okay. So what is a wave? A wave is a continuous disturbance that transfers energy from one place to another with no transfer of matter. And it's always the result of something that's oscillating or vibrating. Every type of wave doesn't actually transfer anything. It transfers energy from one place to another. Imagine you're at the beach and you take your hand and you tap the water on one side of wherever you're sitting, right? You're tapping the water. Now, if you watch, you could see a wave propagate out from your hand. But if you look closely at any one of the particles in the water, the particles themselves are not moving horizontally. They're only moving vertically up and down. Like if I pick any position on this wave, like take a look at this circle right here. This circle only oscillates upward, up and down. But the wave motion that you could see is moving horizontally. What waves do is they transfer energy from one place to another. This section in the water was not oscillating until I started oscillating it over here. And then that energy transferred over to the other section of the water. That's a big idea when it comes to waves. It transfers energy without transferring matter. Okay. So this is a continuous wave. Notice it's always going. The wave is constantly propagating off to the right. But we can also just do a simple wave pulse. A wave pulse is a single disturbance, and that single disturbance travels horizontally. But again, if you pick any particular particle on this, let's say it's a rope or whatever, that particle only moves up and down as the wave propagates to the right. So again, I'll pick this spot here, comes up, comes down, while the energy of the wave moves horizontally. So that's our first two definitions. We have what a wave is. We have what a wave is, a continuous disturbance, and a pulse is a single disturbance that moves off to the right, transferring energy without transferring matter. And I'm talking about waves in general. All types of waves follow these rules, no matter what type of wave we're talking about. Okay. So the first thing I want to talk about is the different groups of waves. There's two different groups of waves that I'd like to discuss. We have our mechanical waves and our electromagnetic waves. What a mechanical wave is an oscillation of matter, and that matter can be solid, liquid, or gas. These waves need something to move through. When I say something, it's some type of matter, right? Some type of medium. That something in wave terms is what we call a medium. A medium is the matter that mechanical waves move through. The medium for ocean waves is the ocean itself. The medium for sound waves is air. And the medium for earthquakes is the earth itself. So we have our water waves. Like I said, if we tap here, the energy of the wave travels through the medium of the water. If water didn't exist, water waves wouldn't exist. We have our earthquakes. If the earth didn't exist, seismic waves couldn't exist. And sound waves. If air didn't exist, sound wouldn't exist because sound propagates through the air. And I can actually prove it to you. I have a little video I'm going to show you live on camera. Let's see. Make it nice and big. There we go. All right. So before I start the video, let me explain what's going on here. It's a little grainy, but what we have here is a bell inside of a jar. And we're going to turn the bell on and you're going to hear it ring. And this bell in the bell jar is hooked up to a vacuum pump. And the vacuum pump is going to slowly suck the air out of the bell jar. And we're going to see what happens with that ringing. Bell in a bell jar. Okay, so we turned on our bell. Our bell is ringing. You could hear the ring. Now we turned on our vacuum pump, and that vacuum pump is slowly sucking the air out of that bell jar. And listen closely to the ringing. You hear it? I'm going to skip ahead a little bit. I don't know about you, but I don't hear you ringing anymore. As that air goes away, the sound cannot escape the bell. There's no sound when there's no air. Now he's going to slowly let the air back into the bell jar. When he figures it out. And there it is. The ringing is back once we have air inside of our bell jar. Sound is a mechanical wave. A mechanical wave needs a medium in order for it to travel. And that medium for sound is air. This is why you might have heard that in space, no one can hear anything that you say. Because in space, there's no air outside of a certain portion of our atmosphere. So no matter what you do with your vocal cords, you won't be able to transfer any sound waves to anyone else out in space. All right, let's go back to where we were. Okay, but that's the big idea for mechanical waves. A mechanical wave needs something to travel through. And that something is what we call a medium, any type of matter that the waves travel through. And the other group of waves that we're going to be talking about is electromagnetic waves. Electromagnetic waves, like the formal definition, synchronized oscillations in both the electric and magnetic fields. These waves do not require a medium and thus can travel through a vacuum. Here's another key physics word here. What a vacuum is, it's a space in which there's no matter present. The way I like to think about vacuum is scientific nothingness. There is nothing inside of a vacuum. But even within that nothingness, electromagnetic waves can still propagate. Electromagnetic waves, in normal terms, is just light. Any type of light is an electromagnetic wave. Now, what we say with these electromagnetic waves is we're oscillating both the electric and magnetic fields. Take a look at this little animation here. The blue is oscillations in the electric field. We discussed electric fields, right? We have an electric field that's oscillating outwards from every type of charged object. I could take that object and start wiggling it up and down. And by wiggling that object up and down, we're changing our electric field. But in the end of our last video, we said that changing the electric field creates a change in the magnetic field. This red wiggle here, labeled B, in physics we used capital B to denote magnetic fields. This is the wiggle in the magnetic field. So by changing the electric field, we're also changing the magnetic field. Light is a three-dimensional wave. We have a wiggle in the electric field, we have a wiggle in the magnetic field, and then it propagates forward through space, transferring energy from one place to another. And because there's no matter that we're wiggling, we're quite literally wiggling the electric and the magnetic fields, light can travel through the vacuum of space. This is why no one can hear you in space, but you can see the light from distant stars out in space. Light from the sun can travel here from Earth. Light from our closest star neighbor, Alpha Centauri, can head our direction. Light from all the different constellations out in space, we can see them because the light can travel through the vacuum of space. Now, I said electromagnetic waves are all types of light waves. Well, what are the different types of light waves? We're going to be diving into this in a future section, so don't worry about it too much here. But this is the entire spectrum of light, the electromagnetic spectrum. Really long wavelengths of light are what we call radio waves. When you're in your car and you're tuning your radio, you're tuning into light waves. In particular, light with a very long wavelength are radio waves. And then as we get shorter, we have microwaves. This is what your microwave uses in order to heat up your food. And then as we get tighter, we have infrared radiation. Infrared is what you feel as heat. When you turn on your stove and you put your hand over the stove, you're feeling infrared radiation. Heat can transfer through an electromagnetic wave. And now in this little sliver, this is visible light. Anything you've ever seen, all of the artwork, all of your favorite books, all of your favorite people, they all exist visually in this tiny little spectrum of the electromagnetic wave. Red is longer wavelength, less energy, and blue and purple are higher energy and lower wavelengths. They're tighter. And then eventually we get to ultraviolet radiation. Again, this is all light, different types of light waves, all electromagnetic waves. Ultraviolet gives you sunburn at the beach. X-rays, that's what we use to see the bones inside of our skin. X-rays can easily pierce flesh, but they don't easily pierce the denser bone inside of our body. So the X-rays bounce off the bone, but go easily right through our meaty parts. And then finally we have gamma rays, which is the highest energy type of light that exists. Okay, again, we're going to dive into a little bit more of this whole electromagnetic spectrum and what it means and how we can maybe make predictions and calculate different things with it. But for now, I just wanted to kind of show you what electromagnetic waves are all about. Okay, so two groups of waves. You have our mechanical waves that need stuff to travel through and electromagnetic waves that do not need stuff to travel through. Mechanical waves need a medium. Electromagnetic waves do not need a medium. They can travel through a vacuum. Okay, so here's just organizing both of those ideas, mechanical waves and electromagnetic waves. Mechanical waves are an oscillation of matter, require a medium, cannot travel through a vacuum. There's no sound in space. And here are some examples of mechanical waves. Any type of oscillation that you've seen in any type of matter is a mechanical wave. This is not an exhaustive list. We have sound, we have earthquakes, slinky waves. Literally, if we stretch a slinky and wiggled it, that's a mechanical wave. Ocean waves and waves through a rope or a guitar string. When I pluck a guitar string, there's a wave that travels up and down that guitar string. And that wiggling of the guitar string wiggles the air around it, and then we can actually hear what the guitar is playing. And then we have electromagnetic waves. We have an oscillation through both the electric and magnetic field. Electromagnetic waves are light. They do not require a medium. They can travel through a vacuum. And as we've talked about, some examples of electromagnetic waves, visible light. Anything that we see is an electromagnetic wave. Radio waves, microwaves, ultraviolet waves, X-rays, and infrared waves are all types of electromagnetic waves. Okay. So that was a lot, but now we have a better idea of what we are actually studying when we study waves. We can study the basics of wave characteristics, but all of those wave characteristics apply to all of this different stuff inside of our universe. Waves are important. Okay, so here are the groups of waves. The next thing I want to discuss are the types of waves. And the types of waves discuss how the wave actually wiggles. How is it actually oscillating that wave? So there are two types of waves that I want you to know. There are transverse waves and longitudinal waves. Before I discuss the definition of these two, just take a close look and see what the difference is between these types of waves. Well, a transverse wave, you kind of see a wiggle up and down. But with a longitudinal wave, you see a wiggle in and out. And the best way to do it is pick a slinky coil and follow that slinky coil as the wave passes. If we look at the transverse wave, freeze it on me, pick this one, comes up, comes down. Right? Comes up, comes down. But let's pick this coil in the longitudinal wave. It moves, what it does is it moves in and then it moves out. Watch closely. Moves in and out. So a transverse wave, any particle inside of the wave oscillates perpendicular to the direction of the wave propagation. The wave is moving this way, the energy is moving this way through the slinky, but the actual matter itself is moving up and down. And for a longitudinal wave, the actual matter itself is moving parallel to the direction of wave propagation. The slinky coil moves in and out as the whole wave propagates off to the right. Okay, let's get these formal definitions down. So for a transverse wave, particles oscillate perpendicular to the direction of wave propagation. If we have a slinky attached to a red wave generator, each particle is only moving up and down. Pick any of these red particles. You could watch them move up and down as you can see that the wave, the energy propagates off to the right. This is a transverse wave. If you've ever been to a sports game and they say, hey, do the wave, and everyone sits down, they wait for the wave to come and they stand up, come down, that would be an example of a transverse wave. We're moving up and down as the wave propagates horizontally around the whole field. Okay. And the other type of wave is what we call longitudinal waves. Particles oscillate parallel to the direction of wave propagation. We're shaken in the direction we go. Pick any particle, but there are some highlighted red particles so you could really see how they work compared to the backdrop, right? If I see any of these red particles, they oscillate back and forth in this parallel to the same direction of wave propagation, right? Notice that none of these particles are actually traveling off to the right. What's traveling off to the right is the grouping of the motion, right? The entire macroscopic motion of this whole system of particles. They're oscillating parallel to the direction of wave propagation. An example of a longitudinal wave is sound. Sound is a longitudinal wave. When I talk, I'm forcing air through my vocal cords, right? And as I force air through the vocal cords, what it does is it starts creating areas of high pressure in the air and areas of low pressure in the air. And as I talk, I'm wiggling the air around my mouth. It wiggles to my phone. My phone picks up that sound wave, and now you're hearing it through your computer or phone, whatever you're listening to me on. Sound is a longitudinal wave. And it's pretty amazing when you really think about it, right? I have thoughts in my head, and I want to take those thoughts in my head and transfer them to you. So I have these thoughts, and then I force air through my vocal cords. I wiggle the air around me in just the right way. That air wiggles your eardrum in just the right way, which creates an electric signal that goes to your brain. And now you can actually understand the thoughts that are in my head through this complex interaction of air and membrane wiggling, right? Like in your eardrum. That's why I like science. It makes you think about things in a whole new way, right? I bet you never really thought about talking and listening in quite that way. Okay, one last thing I want to say about the types of waves, how the waves wiggle. Mechanical waves can be either transverse or longitudinal. So any mechanical wave, like sound is a longitudinal wave, and like ocean waves or transverse waves, right? On a slinky, we can have both types of waves. These are both slinkies, right? We have a transverse wave traveling and a longitudinal wave. But electromagnetic waves can only be transverse. You will never ever find a longitudinal transverse wave. And that has to do with how the electric field affects the magnetic field and how that wave has to propagate through space. All light is transverse. Mechanical waves can be either transverse or longitudinal. Make sure you make a note of that. Okay, so take a second, take a deep breath, make sure you understand all the two different types and the two different groups of waves. What we're going to be discussing next is some wave characteristics, wave basics. When we're looking at a wave, what kind of words can we use to discuss that wave, right? Waves can be kind of complicated. There's a lot of things moving in a lot of different directions. So what terminology can we use to discuss the wave? And how do these characteristics help us identify and characterize what type of wave we're looking at and how that wave affects the universe around it? Okay, so here are the basics of waves. We got the little vocabulary we got to go through. All right, up here I have a longitudinal wave. Over here we have a transverse wave. When it comes to identifying characteristics of a wave, most often, especially in Regents level physics, we'll be looking at transverse waves. But I wanted to kind of show you how it corresponds to a longitudinal wave. Okay? So, the very first thing that we can look at is the crest of a wave. You might have seen this in middle school when we were talking about waves, right? The crest of the wave is the very top of the wave, where we have the location of maximum upward displacement. That's if we're focusing on a transverse wave. You can remember that by saying, like, thinking of the crest of an ocean wave, right? The crest of an ocean wave is the very top of the wave before it crashes down. The crest is up here. And if we wanted to compare that to our longitudinal waves, our crest is the area of highest pressure, or the compression area of our longitudinal wave. Okay, but for now, focused on the transverse wave. The tip-top point is what we call the crest. The trough is the bottom of the wave. That's this spot here. That's the trough. The reason why we call it a trough is because, like, if you ever see like that long bucket that like farm animals eat out of, that's what we call a trough. And that's all down here. It looks kind of like a bucket, right? So the crest is the top, the trough is the bottom. Okay, the amplitude is the height of the wave. The distance from the midpoint to either the top or the bottom of the wave, and that's measured in meters. The difference between crest and amplitude is the crest, we're looking at the location where it's the highest, and the amplitude is literally the distance between this midpoint and the very top of the wave. A common mistake that a lot of people make is they take the amplitude to be the distance between the crest and the trough. That's not true. The amplitude is the distance from the midpoint to either the top or the bottom of the wave. These two distances would be equal, whether I measured from here to the bottom or from here to the top. Either way, we will be getting the amplitude. And because we're measuring a distance, it's measured in meters, just like we've been doing this whole year. Okay. Oh, by the way, when we're talking about the trough, the bottom of the wave, if we corresponded that to a longitudinal wave, the trough, this low area, corresponds to what we call a rarefaction, which is the area of the lowest pressure in a longitudinal wave. You don't have to worry about that much. You won't be responsible for terms like compression and rarefaction, but you will be responsible for terms like crest and trough. And now, the wavelength of a wave. Again, we're trying to get the words to describe how these waves work. The wavelength is quite literally the length of one complete wave cycle. It can be measured from crest to crest, just like it is on this diagram. This is one wavelength. And I could take a meter stick, right? I could take a meter stick, lay it over, and see how far this distance is. It could also be measured from trough to trough, but it's really any 2 points in the wave that are what we call in phase. And we'll be talking about that, what that means in a second, what in phase means. So because we're measuring a distance that's measured in meters, and in physics, when we're doing calculations, we denote wavelength by the Greek letter lambda. And draw on my TV again. What lambda looks like is a straight line with kind of like a little wiggle. That's the Greek letter lambda. So if I say lambda equals 1 meter, that means we have a wavelength of 1 meter. we're going to need to use wavelengths to make some calculations later on. Okay, destroying my TV slowly. Okay, what this diagram shows us is it's showing you that no matter which 2 points I pick, as long as they're in phase, crest to crest, trough to trough, or these 2 locations here, we're seeing the distance for one total wave cycle. And no matter, as long as I pick 2 points that are what we call in phase, we'll talk about that in a second, we're always going to get the same wave length. So you can pick any 2 points. I always like to use either 2 crests or 2 troughs, but this is totally reasonable as well. 2 points in phase will always be equal to the length of one wave length. If we change the wavelength of the wave, we've changed the characteristics of the wave. If we change the amplitude of the wave, we've again changed the characteristics of that wave. So it's important to understand what these words mean, and later on we'll talk about what it means to actually change these quantities and how it affects how these waves affect the environment around us. All right, so I kept saying that word phase, right? Let's talk about what phase means when it comes to waves. What phase means is what the wave is doing at that particular point. What that means is, what is that particle truly doing at that point in the wave, right? So if you have the wave traveling this way, right, you want to think of what that particle is actually doing, or what direction is the wave heading in that point. Any 2 points on a wave is said to be in phase if they're doing the same thing. Now notice this isn't really like a super formal definition of what phase is, but this is how I understand phase, and I feel like this more informal definition will help you better understand what's going on with phase. What is the wave doing at that point? If they're doing the same thing, the 2 points are said to be in phase. Point D and point I are in phase because they're both crests on this wave. Points A and point J are also, point A and point F are in phase. Notice that this location in the wave is kind of heading upwards, right? And at point F, the wave is heading upwards. Points A and point E are not in phase because A is heading upwards, E is heading downwards, right? If I was tracing out the wave, right? Since my pencil moves upwards at point A, and it also moves upwards at point F, those 2 points are in phase. E and J are in phase because if I was drawing the wave, my pencil moves down at E, and it also moves down at J. All right, 2 points in a wave are out of phase if they're doing different things, right? A and B are out of phase. Yes, they're both heading upwards, but they're not quite in the same location, and they're not doing the same thing at that point, right? C and D are out of phase. E and F are out of phase. But there are also points which we call perfectly out of phase, which means they're doing opposite things at these points. A and E are perfectly out of phase because A is heading up, E is heading down. Any points that are perfectly out of phase are half wave cycles apart from one another, where points that are in phase are one wave cycle apart from one another. Notice A and F are one full wavelength away. E and J are one full wavelength away. A and E are half a wavelength away. Okay, it's important to identify. If we go up and go back down, that's half of a wavelength. We also need to go all the way down and back up to get one full wavelength. Okay. So, I hope you're feeling okay with that terminology. All the different words we use to describe waves, the groups, the types. Let's put all of this together and try a problem. I'm going to give you a wave, and we're going to see if we could identify what's going on. That's going to be this problem here. But before we talk about that, I identified points on a single wave that are either in phase or out of phase, but we can have completely different waves and discuss if these waves are in phase or out of phase. Notice we have this red and blue wave. Up here, the red and the blue wave are perfectly on top of one another. That means these two waves are in phase. If we have this red and blue wave here, you can see that the troughs are not quite lined up, crests are not quite lined up. These two waves are out of phase. And if you look down here, these two waves are perfectly out of phase. So when we're talking about in phase or out of phase, we could look at points on a single wave, or we could look at two completely different waves and discuss, are these waves in phase? Are they out of phase? These two waves are completely out of phase because at any 2 points, these two waves are doing opposite things. Even at the cross, blue is heading down, red is heading up. All right, so hope you're feeling okay with all that terminology, all those different definitions. The beginnings of waves is very qualitative. A lot of vocabulary, a lot of understanding of subjectively how these waves work. Soon we're going to be actually diving into some mathematics behind waves, calculating how fast waves are going, using that to calculate wavelengths and things like that. But before we do that, let's analyze a particular wave. We're going to use all of the tools that we've learned over this whole lesson to analyze this wave down here. Some points on the wave are labeled. We have A, B, C, D, E, F, G, H, and I, all on the wave. And some information is also given about the wave. The distance from A to G is 15 meters, and the distance from I to D is 2 meters. Let's see if we can use that to answer all the questions here about this wave. This is a very standard physics thing to do. Yes, this is one question, but there are H parts to the question. You see that a lot if you continue your study of physics. So the first question is, what type of wave is this? Now remember, when we were talking about waves, we had two different types of waves. And the type of wave describes how the wave wiggles. Is this a transverse wave, or is this a longitudinal wave? Well, going back to our definitions, either rewinding the video or just thinking it through, transverse waves had the particles in the wave moving perpendicular to the direction of oscillation, where a longitudinal wave had particles moving parallel to the direction of propagation. As you can see, this wave, any particle in the wave is going up and down as this wave propagates. So this is what we call a transverse wave. The answer is transverse. If you got that right, give yourself 10 Hatzfeld points. Well done. Okay, how many cycles of the wave are shown in this diagram? Well, when it comes to a single wave cycle, one wave cycle is one complete wavelength and from any 2 points in phase. So if we look here, it can't be one cycle, right? Because B to F is one wavelength, and I have these two little extra portions here. So we have more than one cycle. Well, another way we could look at this, if I go from A to E, that's one cycle. But then we have this extra little hump here. And if we look, the hump from A to C is 1/2 of a wave cycle, right? Here's half, here's the other half. From A to G, we have one wave cycle and an extra hump. So the number of cycles that are shown in the diagram is 1.5 cycles. There is 1.5 wave cycles shown on this diagram. Okay. Now, so putting this on pause for a second, I know this seems like a lot, but if you really take the time to understand how these waves work, that'll help you better understand how art works, how music works, all of the things in our universe that we really enjoy as humans, that make us humans. A lot of it can stem from how these waves work. And I think it's pretty amazing that your favorite song could be translated to a waveform. And we could talk about the amplitude of the waveform, the wavelength of the waveform. And that unique signature of the waveform is your favorite song. going back to the problem. What is the amplitude of the wave? Well, based on the information that's given and our understanding of what amplitude is the distance from the midpoint to either the crest or the trough. So, the distance between B and H would be the amplitude. It's not the distance between I and D. This would be two amplitudes, because the distance from the midpoint to the crest or the trough. Well, they told us that the distance from I to D is 2 meters. And if that's two amplitudes, then the distance from B to H, which is a single amplitude, has to be this divided by 2. The correct answer is 1 meter. The amplitude of this wave is 1 meter. Okay. Now, what's the wavelength of this wave? Well, wavelength is the distance between any 2 points in phase. B to F, A to E, C to G. Those would all be one wavelength. Okay. Well, they said that the distance between A and G here to here is 15 meters. And we also know that this is 1.5 wave cycles going from A to G. Well, if it's 1.5 wave cycles, that means that the wavelength is going to be from A to E, like I said. So if this is 15 meters, that means A to C is 5, C to E is 5, and E to G is 5. So one complete wavelength has to be 10 meters. 15 is 1.5 wave cycles, so 10 meters is going to be one single wave cycle, or the wavelength of this wave. And these types of waves can exist, right? Remember that a meter is about 3 feet. We could have a wave with an amplitude of 1 meter and a wavelength of 10 meters. This could be an ocean wave. It could even be a light wave. These specifications work for, this would be like a radio wave that you actually tune your radio to hear your favorite radio station. Okay, moving right along. Part E says, which point or points show a wave crest? A crest is the topmost point of a wave. And if we look, we can see that point B is at the tippy top and point F is at the tippy top. B and F are both wave crests. So which point or points show a wave trough, the bottom of a wave? B and F are crests. Here we have a bucket down here. So point D is a trough of a wave. All right, hope you're feeling okay so far. We have a few more parts to go, and then we're done with this video for today. Which points on the wave are in phase? Which points are doing the same thing? Now, this is a little overwhelming at first because we have all these points that we're looking at, right? So what I like to do is I like to pick a point and see if there's any other points on that wave that are doing the same thing. At point A, if I drew a little arrow, the wave is like kind of heading upwards at this point, right? So A and C are not in phase. This is only a half a wave cycle, and C is kind of heading downwards if I was drawing this with my pencil. But E is also heading upwards. A and E are in phase. C and G are also in phase because my pencil's heading down at C and it's heading down at G. And finally, B and F are also in phase with each other because they're both wave crests. They're both doing the same thing at that point. Okay, so the correct answer, we have A and E in phase, B and F in phase, and C and G in phase. Now these are separate lists. A and E are not in phase with B and F. A and E are in phase with each other, B and F are in phase with each other, and C and G are in phase with one another. And finally, which points of the wave are perfectly out of phase? Which points are doing opposite things? in the wave? Well, A is heading up, C is heading down. Those are out of phase, right? But remember, A and E are in phase. And if A is perfectly out of phase with C, that means E is perfectly out of phase with C. A is perfectly out of phase with G. So that means that E is perfectly out of phase with G. Which points in the wave are doing opposite things? See if you can find them all. And the correct answer is here for part H. Points A and E are perfectly out of phase with points C and G. These are out of phase. Also, points B and F are perfectly out of phase with point D. B and F are crests, D is a trough. These are half of a wavelength away. So both B and F are out of phase with point D. Okay. So hopefully this example helped hammer home some of the wave characteristics that we discussed. What we're going to be discussing in future videos is calculating how fast waves move, because you could see that even ocean waves can move at different rates through the ocean. Sound waves can move at different rates if we have different types of air that it's moving through. So we have a lot more to discuss with waves. Eventually, we're going to be getting into how instruments work, how each instrument sounds very particular because of how it's manipulating the sound waves, how it's manipulating the air in and around that instrument. All right, so we have some more to discuss. Make sure you understand the basics here because we're going to need the basics moving into more complex topics when it comes to waves. Okay, hope everyone's doing well. And I will see you in the next video.